The equipment we will need for this experiment includes a rectangular loop, a solenoid or coil, and also a circular loop. We will then additionally need a black lead with a double cylindrical connector and also a black lead with a cylindrical connector at one end and a crocodile clip at the other end as well. A red lead fitted with a cylindrical connector and at the other end a crocodile clip, and finally a red lead with cylindrical banana connectors at both ends as well. Let us proceed by gently shaking the coil and the solenoid in order to distribute the iron filings contained within the plexiglass section in a suitably randomized manner. Let us proceed by observing in some detail how to connect the cables to the ScienceBus. Let us take the black lead, which is fitted with cylindrical banana connectors at either end. Let us now take the second cable and carefully insert its cylindrical connector fully into the connector of the first cable, making sure that the crocodile clip connector remains free and completely unobstructed at the other end. We shall repeat exactly the same procedure for the red leads as well. We take the red lead that is fitted with a cylindrical banana connector at both ends. We insert one end fully into the red port of the ScienceBus, and into the free end we then carefully insert the banana connector of the second wire, thus leaving the crocodile clip connector completely free and unobstructed at the other end. I shall now proceed with the experiment, and then we will return to the ScienceBus settings in order to adjust the volts and the amps. We shall then proceed to connect the crocodile clips both securely and firmly to the first coil. This is the circular coil, so please connect the red crocodile clip very firmly and securely to the red screw, and the black crocodile clip to the screw that is clearly marked in green. Let us now switch on the ScienceBus current generator and carefully observe that, when the current flows through the loop, the iron filings will align themselves neatly along the magnetic field lines. To carry out this experiment and thus to observe the movement of the iron filings, a potential difference of 5V and a current of 0.6 A are entirely sufficient. Indeed, an excessively high current could potentially damage the conducting wires. Let us now repeat the experiment once again while changing the camera angle slightly. We therefore repeat the experiment and observe that at the very moment the current is switched on, the iron filings spread outwards and align themselves neatly along the magnetic field lines. Indeed, when an electric current flows through a loop, such as the circular loop shown here, it generates a magnetic field in the space around it. The experiment therefore allows us to clearly observe the orientation and direction of the magnetic field lines. The magnetic field generated by a circular loop that carries an electric current is perpendicular to the plane of the loop, and its direction is determined by using the right-hand rule. At the very center of the loop, the magnetic field reaches its maximum value and remains perpendicular to the plane of the loop. The field lines in this region are almost straight and nearly parallel to the loop's axis, indicating a largely uniform field. Along the axis of the loop, the field gradually decreases as the distance increases. As you move towards the edges of the loop, the field lines begin to curve more noticeably, linking up with the external regions. Outside the loop, the field takes on a shape similar to that of a magnetic dipole. Indeed, the field lines will tend to close. The right-hand rule makes it possible to determine the direction of the magnetic field in relation to the direction of the current flow. Finally, it is indeed possible to determine the magnitude of the magnetic field at the very center of the loop. In fact, this is given by Biot-Savart's law. And this shows that the magnetic field calculated at the very center of a circular loop is directly proportional to the current flowing through it. Therefore, the greater the current, the stronger the magnetic field will be. It is also inversely proportional to the radius of the loop. Therefore, the larger the loop and thus the greater its radius, the weaker the magnetic field calculated at its center will be. Let us now change the loop and instead use the rectangular one. When we switch on the current generator, we observe that the iron filings will arrange themselves neatly and clearly along concentric lines around the side of the loop. This is in accordance with the Biot-Savart law. Let us review the experiment from a different perspective. Finally, let us now take the solenoid or the coil and observe carefully how the iron filings align themselves inside the loop once an electric current is flowing steadily through it. We then switch on the current generator and observe carefully how the iron filings arrange themselves neatly along the magnetic field lines, which in this case are straight and parallel lines inside the solenoid, clearly indicating a uniform magnetic field. The strength of the magnetic field inside the solenoid can be determined using Ampere's law, in which nin denotes the number of turns in the coil and il represents its length. Let us repeat the experiment once again to observe the arrangement of the magnetic field lines clearly.